The slides weren't advancing now. Do it again. Yeah. All right, let's do it again. My name is Taylor Doherty from the Division of Allergy Immunology, and welcome to Medicine Grand Rounds. Today, we are honored to have the 6th annual Steve Wasserman Lectureship. Few words about Dr. Wasserman. He's a renowned leader, mentor, educator, clinician, and scientist for over 50 years. He founded the Division of Allergy Immunology after moving from Harvard in 1979, where I'm told that he was associate professor for exactly 1 day at Harvard before he came. I had to bring that out, Steve, sorry. And he was also the Helen M. Rainey Chair of Medicine from 1988 to 2001. He is the former president of the American Academy of Allergy, Asthma, and Immunology, as well as the American Board of Allergy Immunology. His scientific impact is profound, including mast cell biology, allergic mediator release, airway disease, and innate immunity. 2019 was our first annual Wasserman Lecture with Dr. Frank Austin, and since then we've been able to bring world-class investigators to speak at Internal Medicine Grand Rounds, and we hope this will continue, and we know it will today, because we are honored to have Dr. Charlotte Cunningham-Rundles from Mount Sinai to speak to us today. And for the introduction of our speaker, I'm going to have Dr. Takisa Smith from our division give a quick intro. Thank you.
Good afternoon, everyone. It's with great honor that I introduce Dr. Charlotte Cunningham-Rundles at this year's Wasserman Lectureship guest as the speaker. Dr. Cunningham-Rundles is the David S. Gottesman Professor of Immunology at the Icahn School of Medicine at Mount Sinai in New York City, where she also holds the distinction of both Professor of Medicine and Professor of Pediatrics. She established and directs the Immune Deficiency Program at Mount Sinai, which is widely known as one of the country's leading referral centers with the aim to evaluate and treat infants, children, and adults with a vast array of primary immune deficiencies. In addition, she established a therapeutic infusion service and serves as the director. She has been the program director of the Allergy and Immunology Fellowship Training Program and previously served as chief of clinical immunology at Mount Sinai. Just to highlight her background further, she is a graduate of Duke University, where she earned her Bachelor of Science degree in zoology and chemistry, medical doctorate at Columbia University College of Physicians and Surgeons. She completed her internal medicine internship and residency at Bellevue, New York University Medical Center, and earned a Ph.D. in immunology at New York University. Her research, supported by the NIH for several years, has been focused on cellular, molecular, and genetic defects in antibody production. Not only is she a distinguished and globally recognized physician scientist with over 200 publications in high-impact journals and an author of several book chapters, she's an award-winning physician often recognized for her clinical acumen and care. She is a past president of the Clinical Immunology Society and has served on the board of directors of the American Academy of Asthma, Allergy, and Immunology. In recognition of Dr. Cunningham-Rundles' exceptional contributions, the foundation by the same organization has established the Charlotte Cunningham-Rundles Lectureship, named in her honor. For 5 years, this lectureship will fund an annual lecture by a distinguished scientist or clinician selected for their shared passion for advancing immunology and patient care. Dr. Cunningham-Rundles has served on review committees at the NIH, NASA, the FDA, and was founding member of the consortium called USID-NET, which stands for the United States Immunodeficiency Network, and was established to advance scientific research in the field of primary immune deficiencies. She serves on the medical advisory boards of the Immunodeficiency Foundation and the Jeffrey Modell Foundation, serving as a longstanding member. Dr. Cunningham-Rundles is currently an officer of the Expert Committee on Inborn Errors of Immunity in the International Union of Immunological Societies, which is an umbrella organization for many of the regional and national societies of immunology throughout the world. As her former clinical fellow, I have seen the direct impact Dr. Cunningham-Rundles has had scientifically, philanthropically, and policy initiatives pertaining to primary immune deficiencies. She's responsible for inspiring and launching the careers of numerous scientists and physicians, myself included. With no further delay, I'd like to introduce Dr. Cunningham-Rundles, who will be giving today's talk entitled Antibody Deficiency, Learning from Our Patients.
Now that you've gone on and on, we can finish. Thank you very much for inviting me for this really wonderful event. I'm going to try to figure out how to make the slides go to the next one. Oh, this is easier. Get out of here. Okay. So antibody, learning from our patients. This is actually a scene in Mount Sinai. It's opposite Mount Sinai in case you come to New York. This is Central Park, and that isn't Mount Sinai. That's just the apartment building, which is opposite. But anyway, that is our view. So thank you very much, Dr. Wasserman, for making these group come together. It was quite a number of years ago that you had the vision to do it, and it means that that's really why we're in this room today. And that's why the Academy, for example, thanks you for all the work that you've done, and also the boards of ABA-IM. That's the same story. It's extremely important for us to get together. I know COVID has made it harder, but I think I'm very grateful for also the opportunity to actually come here and talk to everyone in person. It's really a great honor for me. You've heard a lot of things, but I particularly wanted to thank Dr. Wasserman for making this occur. He was the catalyst for all of these events, you know, so this is something which is very important. These are disclosures. I'm not going to go into any of the issues there, but I was going to ask you, first of all, is kind of a question. How many people in this room had a vaccination in the past 6 months? I thought that I would find that, and I expect the people at home in their Zoom room to also raise your hand, because I suspect that almost everyone has also had a vaccination. And I think that in a way, from the immunological point of view, we talk about allergy, asthma, immunology, but the eye oftentimes gets kind of short shrift because you keep thinking antibody, oh, well, we do it. Oh, well, you know, we get a vaccination and it happens and it's no big deal. Put the shot in your arm, goes to the lymph node makes IgM, splits to IgG, and first thing you know, hey, you're this presto magic, you're protected. You know, the honest truth is that there's a heck of a lot more to it than that. And if you think about it, I'm just going to probably mention a few of the things that you probably don't know about how it is this works. And number two, the things that we honestly don't understand at all. First of all, everybody understands that globulin is about 20% of your serum protein, first of all. So that's an awful lot of protein to be making every single day and to be carrying around. It takes a lot of energy, right? It takes a lot of energy to do that. And that's done by plasma cells, and plasma cells in the bone marrow secrete about 10,000 molecules of IgG per second. Now, I did not measure that. That's Hans Dosch in Canada measured this, and it's been a kind of a known fact. If you go back and you look at this particularly stunning effect, you think what you have here is you have really kind of a factory. The thing that we're not talking about, and I don't think it comes up right on these slides because I didn't have time to put everything in it. If you happen to know how long plasma cells live, they can live as long as you do. So if you're 50 years old, some of your plasma cells are 50 years old. When your plasma cells are instructed to do their job, they're going to do it forever. They're going to continue to do it. They do not divide. They stay in your bone marrow in a very specialized niche, which people don't even understand how this happens. And they can live as long as you do. So 100-year-old is going to have some 100-year-old plasma cells. There's no other cell that lives that long aside from neurons. So in a way, when we say antibody memory, I really mean it. It's memory of a very specific sort. It's a very interesting sort of a parallel fact that we know is actually the case. It's a very, very stunning notion. But what can go wrong? For most people, nothing. Everybody in this room made their antibody. That's great. That's really cool. But what happens, and how is it that we make this thing work? How is it that all this gets assembled? You have to think every time you make an IgG molecule, you're actually assembling the components of 3 different disparate genes. The heavy chain and the light chain has to come together in one location and then be assembled and then secreted and kept then in the plasma cell for a very long period of time. So what could go wrong? Well, you could have no B cells. That's easy. You know, A-gamma globulinemia, we understand that. No B cell activation, no maturation, no plasma cells, and maybe no antibody production. And you say it that way, it sounds very simple, but in fact, that is a tremendous number of steps here. Now, going way back, I think everybody here probably knows Colonel Ogden Bruton of the Army, right? He was at Walter Reed. And the thing that every time you look at this report, there's some things about this report that are very interesting to sort of open up this box, which is that, first of all, this was an 8-year-old boy, and you wonder, he's A-gamma, he's 8. You're not supposed to live to 8 if you don't have any gamma, right? So how come he lived to 8? The other thing is, if you look at the report, he's had 19 episodes of pneumococcal sepsis. Don't you think that would have wiped him off the map already? Should have done, it didn't. Now, the other thing, which is the story, which is also not currently or commonly known, is that Bruton did not know at that stage, you know, what was wrong, of course. And he contacted his friend, Arndt Azelius, who at that time had established a electrophoresis machine in one of the many other rooms at Walter Reed. And he said, well, he's probably going to have a gallon of gamma globulin in his blood. It's just going to be packed, right? Because he's had so many infections. I'm sure there's going to be a lot of gamma globulin. And what happened? Well, Azelius called him up and said, by the way, there's no gamma globulin in this boy's blood. And kind of an interesting thing was that the machine was at the right location at the right time for Dr. Bruton to figure this out. And for him to be able to take then the concentrates of gamma globulin and say, if he doesn't have any, I guess we're going to give him some. And so this was the first use of gamma globulin really in the United States and perhaps even in the world. It was really a very, very interesting sort of phenomenon. Now, the other thing is that we commonly order, and maybe even today you've ordered quantitative immunoglobulins on somebody. You've probably already done that. But how did people do it back in 1952? He didn't have any radial immunodiffusion or nephelometer. What he had was this moving boundary electrophoresis that was invented in 1930 by Dr. Azelius. And after that, then came the Kaplan flocculation test. That was by Henry Kunkel in 1947. Electrophoresis was finally 1952. Radial immunodiffusion was 1965. Rocket immunoelectrophoresis was 66. And then finally, nephelometer was 1971. And finally, additional methods, you know, with the radio scattering and, you know, particle dispersion is finally 1978. So measuring gamma globulin was not a simple process back in 1952. And in fact, it wasn't even that simple in the following several decades, as you can see. We take it for granted. It's very easy for us to do. But as you can see, it actually had a long history of its own. So here comes a little boy, and everyone now thinks, okay, that's interesting. But then subsequently, there were other cases reported, almost always children. And by the way, I want you to notice something. Every single person here is a pediatrician, right? Fudenberg, Good, Goodman, Hitzig, except for Kunkel. Kunkel was not a pediatrician. Evan Roy, Rosen. All these are pediatricians. And so all the original reports about primary immune deficiency are coming from the pediatric side of things, right? So the congenital defects of immune system were first put into some framework. This was a very large meeting on Sanibel Island in Florida in 1971. And then all of a sudden, something else happened, which is that what you have in 1954, Jay Sanford in Boston at Mass General says, we have a 44-year-old woman, wrong age. She's an adult. She's the wrong sex too, by the way. We were thinking up until then it was a boy thing, right? They thought it had to be little kids. So she's 44, she's got no gamma globulin. What on earth are they talking about? So it turns out, of course, this is in the New England Journal of Medicine. And this is the first report, really, of the common variable immune deficiency, what we would now call that. So it's a very kind of curious thing. That's why it was written there. But when the team got together with all these reports coming together about various immune deficiencies, then they had to come up with some way to name them because most of them were children with this one outrider of the lady that was in Boston. And they already knew that T cells had been invented. By the way, you probably don't realize that T cells weren't invented and B cells were not invented until very shortly before 1971. In other words, nobody had named them as such because they were not distinguished as such, remember? They were just, small lymphocytes. And by the way, they were said to be very undistinguished morphologically. That was another kind of thing that one of the authors said. Lymphocytes are very undistinguished morphologically, but we don't feel that way these days, do we? Anyway, the naming of these defects was then according to either T cells or B cells. Severe combined immune deficiency had already been described. And they were then making an attempt to divide these into these categories here. And take a look at that bottom. These are the antibody deficiencies, but look at the last one. Variable immune deficiencies common, because by that time a few others had sort of arrived, a few other adults, and largely unclassified. And I'm sorry to say that's exactly where the current common variable immune deficiency name comes from, is this report. I don't like the name any better than you do. Is it common? I don't know. How often is it? We don't know. We don't know how common it is. Largely unclassified. Yeah, I guess that's kind of true, right? So we don't care for it. Yes, it's variable, but it's the worst name in the world. On the other hand, this is where it came from. It came from this really one report. We've never really gotten any better. This is the latest update of the IUS report. We met recently. We will on our web pages have a newest update about the current listing of all the primary immune deficiencies. The table that I am the most responsible for is actually the B cell deficiencies, and that's why I'm on there. It's now headed by Isabel Metz and Stuart Tangy. We get together every year or so in order to come up with our newest report of all the current divisions. And we pretty much go along the same divisions as we had done in that original Sanibel Island report, except a little bit more expansive, partly because now we would divide it into the B cells, the T cells, the NK cells, innate lymphoid cells got added, of course, neutrophils, and of course, the stem cells. And so in a way, the overall framework has stayed the same. I like it in a way, but I also have to tell you there's a lot of trouble with it, and I'll tell you why. So first of all, take a look at the way that it's divided. This is just almost exactly the way the original report was, except that we can see that what we have at the bottom are the autoinflammatory disorders. Like, where did they come in? Number that one there. Complement, that's easy. We got complement. We understand what you're talking about. Bone marrow failure. Okay, so that's adding in some of those genes we now would consider a cancer gene, right? Bone marrow failure, some of those. And then phenocopies, right? What the heck is a phenocopy? So phenocopy is going to be thymoma, for one. It's going to be that thing where you make an antibody against your interferons, right? The antibody against GCSF, your antibodies against interferons. So those would be the ones that are going to be acquired. So in a way, we're kind of straying away from the genetic. We're now moving over into pretty much everything we can think of to throw into this pot. So it's reasonably okay, except that there's going to be some issues I'm going to come to in a moment. So these are the current defects and the current ones. For table 3, we only added 2 new genes this year. So that means people aren't working hard enough on B cells, according to me. Okay. But some of the others have really gotten a lot more attention. For example, the autoinflammatory diseases have gotten more. But the answer is now there is about 550 of these primary immune deficiencies. And so when you're thinking about the types of defects and you need a reference, this is probably the one you're going to end up using. Okay, that's great. Now you're in clinical practice. The overall prevalence of immune deficiencies, and this is now Mount Sinai's data, but it's actually just the same from the textbook that Kate Sullivan now does, that was the old Dick Steam pediatric diagnosis book. It's exactly the same table. It comes out to be pretty much the same. In other words, if you're talking about, you have a new patient and you're thinking it might be an immune deficiency, if you're thinking like a doctor, you're going to say, what's likeliest? What's the likeliest thing? Where am I going to spend my patient's money? What am I going to order first? What am I going to think about first? And what I want you to think about first is the antibody defects. Because honestly, this is where the money is. This is where the majority of your patients are. So if you're getting ready to go into practice this year or next year and sometime in the next few years, if you want to stay in business, you can always go to the antibody deficiencies and see plenty of them. So that's just a word to the fellows. Because you're always going to have business. You're always going to have people who want to know what's wrong with them. So this is the tables currently, the antibody deficiencies. It's table 3. And you have, as you would have expected, the A gamma globulonemias, the ones with the low isotype CVID. Number 3, the hyper IgM phenotypes, right? And then number 4, where you're lacking either an isotype, an IgG2, for example, or you're lacking a happy chain or a heavy chain, or you have really normal numbers of lymphocytes, but it would be also including IgA deficiency. So that would be the last one. And then diseases of immune dysregulation. Okay, so far so good. It's pretty tidy, but I'm going to show you why it doesn't actually work 100% the way you think it should. So these are the antibody deficiencies, and you can kind of make this nice table that just says, okay, where are you? Where are these diagnoses? And you can see that the A gamma globulonemias are going to be genetics that affect the early development and moving all along. The hyper IgM will be affecting those that are going to go through isotype switch and forming germinal center. The CVID is almost a smear, isn't it? Starting from the immature B cell all the way over to, oh gosh, I just couldn't finish with that memory. I just couldn't finally make that plasma cell for you. That's the only thing wrong, IgA deficiency and G deficiencies and such. Now, what's the point I wanted to make? One of them I wanted to make is that these are not children. The average age is 20 to 40. This isn't just my data. This is US data. This is ESID's data here, the European Society of Immune Deficiencies data. Thanks. And this is the data also from Mount Sinai. The females were diagnosed average age 36 and males were averaged about a decade younger, you know, perhaps. But these are not children is the most important thing. And you think, you have somebody who has very little gamma globulin, and this is one of the quandaries, right? And your IgG is like 50, and you're 46 years old. How did you do that? How did that happen? Did your B cells just go out of business? Or when did they go out of business? Or maybe your T cells are wonderful and they're taking all the freight. You know, there's a lot of mystery about why it is that you can get away with not having enough antibody for a very long period of time. We still have to sort of cope with this idea. And all of us in business have seen patients that show up rather later than they should have done, exactly for this reason. So there's a mystery that has not been solved. Some of it, I think we have a vague notion. For example, some of the Icaros defects seem to affect B cell development over time. So over time, they slowly deteriorate. And this could be true for Icaros, could be true for the others, but we haven't proved it because we don't have that capacity of really figuring it out. But this is what I do want you to know, which is the average diagnostic delay is somewhere about 9 to 10 years. In other words, the patient's had a pneumonia and a pyema, a bacteremia, a meningitis, or something relatively major. And they won't be diagnosed for 10 years because nobody has bothered to take their quantitative immunoglobulins during this period of time. How much does quantitative immunoglobulins cost? Anybody know? Make a guess. $50, $60, maybe $70. How much do you think an empyema costs? More. And decortication, let's not forget that part. So in other words, it's not just me who says this. This is actually the Frontiers of Immunology. This is European data, which say that what you have is a lot of missed patients. And we continuously see this problem. And so it's our job to actually get better at it. And I think that's what, you know, the whole idea about trying to get earlier diagnosis, even after that person has had their cardinal event, is something important. Now, CVID actually has a definition. It's not super duper. It's not wonderful, which is that you have to have a low IgG. You have to have IgA and IgM low and or IgM. Usually it's IgA. And you have to be not a baby anymore. Helen Chappell's thinking 4 years old. I think, you know, at least over 2 is what the definition was. But you cannot be an infant anymore because, in fact, it could be just physiologic immaturity. And you really have to check out the antibody function. In other words, if the IgG is 100, there's probably no use to spending a lot of money trying to measure antibodies because they don't have any gamma globulin to make an antibody with. On the other hand, if the IgG is like 200 or 300 or 400, you probably want to spend some time making sure that you actually know that that person actually doesn't have anything functional there. And then the last one is even more important in a way, which is you have to say, well, is it GI loss? Is it steroids? Is it lymphoma? Could it be something else? You know, let's just make sure that we are on the right page here. So this is a cartoon in the New Yorker, but I put my own label on it. Which is that, you know, for the last 50 years, we've called it CVID, and we've just said, you know, hey, shove it in that bag. We'll call it a CVID and go away. We'll give you some gamma globulin, maybe some antibiotics every once in a while, and then shoot. You know, then we'll just let somebody else deal with that. But question is, you know, for people like you and me, what we want to know is, well, why? Why did those antibody cells not make it? What's the story? And as you know, BTK and CD40 ligand were first described in about 1992. So here it is, you know, we're up at 2024. Actually, I didn't update this slide with the final date over there, but I put most of the genes on there. And that is that we're now got all the ones in yellow are the ones that contribute to making a patient with common variable immune deficiency. And it's really an odd mixture of genes. And I'm going to tell you where they lie in a moment, but it comes from a lot of different locations in the immune system with different functions. But as you can see, we had to wait quite a while for the early pediatric diagnoses to catch up with the ability to go over and say, okay, here's some genes here. Now look at the ones that were 2002, ICOS and TASI, for example. I'm going to talk about those in 2 seconds because they kind of broke the ice, I would say, which is that let's just talk about how things actually, how does this work get done? How does it happen that you can make an antibody and last the entire lifetime of that antibody? So those two genes are interesting. And the ICOS deficiency patients were first described in a group of 5 families that all live along the Danube River, and in most cases were related. And you can think of how that could have happened, okay? Anyway, what we have is these families here. This is another paper by Bodo as well, Nature Immunology. And this was interesting because you can see ICOS is really actually on a T cell. So what you have is inadequate T cell driven activation of that B cell, a little bit like common variable immune deficiency, but it's a little more like hyper IgM syndrome. So it said, you know, it doesn't have to be the B cell's fault. I think for about 20 years there, after BTK was discovered, people then ended up thinking, well, it's probably the B cell's broken in some ways. They spent a lot of time looking at B cell genes. But in fact, that wasn't where the money was. The money was going to be elsewhere. And I'm going to talk about that a little bit more in a moment. So this is the ICOS. And of course, that sort of says, okay, this is interesting. This tells you another way that you could not have adequate stimulation of your B cells. And that tells us one more thing. Now, I have never seen an ICOS deficient patient. And mostly this is a recessive gene as well. So chances are you may or you may not. You probably won't, actually. In the United States is very unusual. But the second one that came about, and this again, in this case, happens to have been from the German group, again, from Bodo Grimbacher's group. But this is our work from which we collaborated with Bodo in that year, which was that we had a great number of CVID DNA. And I was wanting to know, well, how many TASI mutations do I have? The TASI is actually a TNF receptor. And he had discovered, Bodo and group had discovered that that gene, which is a B cell intrinsic gene, was abnormal in quite a number of patients. And we did as well. We found it to be true in about 7% of our patients. And the other thing that we found was interesting was that they were commonly the same mutations in different families, genes that were either having to do with the binding zone or a transmembrane region. But when we did find it, it was likely to be associated with a very big spleen, portal hypertension in many cases, lymphocytic infiltrates, and previous history or current history of autoimmunity or previous splenectomy, for example, autoimmune hemolytic anemia or neutropenia or all of the above. And so it's associated with extreme amount of immune dysregulation. But the people looking at TASI these days think, yeah, it's not that important because 1% of normal humans have this gene too. You go out and look at DNA banks, it's not an uncommon gene in the regular population. So in other words, it's autosomal dominant, except that it's got such variable penetrance, it's hard to pin it on it. Just that when you do see it in a patient, it's likely to exert a certain phenotype. So it has a rather strong voice here. Even though it's not the only voice, it certainly is a strong voice. And these are the TASI deficient, genes here. TASI is secreted it's present as a trimer on the surface of B cells, and is necessary for binding to these ligands, APRIL and BAF. And both of them drive B cell production and that sort of thing. But as I say, it's confusing because family members with the same mutations can be perfectly healthy. And chassis defects are a little bit too common. So one of the major questions now, and there's a paper that's just been submitted to Frontiers that, tries to address the issue. Okay, cool. What other factors then, please? Assembling a very large international cohort of chassis deficient patients saying, tell me what other genes have a voice. So that's going to be an interesting paper to look at. We contributed, obviously, our DNA to that study. But this one's a little bit out of left field here. This is NF-kappa B1. And this is our paper in the Journal of Experimental Medicine a couple of years ago. And that was actually first discovered in Europe, which was that NF-kappa B1 mutations were found in about 8 to 9% of CVID patients, which is an astronomical number. Now, the thing is, the reason why this paper is particularly useful, I think, is that you can find these mutations of NF-kappa B1 in a lot of patients. The catch is that the red ones are functional and the blue ones were not. In other words, they did not seem to be deleterious. So it depends where in NF-kappa B1 the activation defect is. And this is a really good slide, and you keep it in your clinic. You can take a look at it when you interpret your data from in vitae or from any whole exome sequencing. Just handy to know, is it one that has been incriminated or one that has not been incriminated? It's just useful that way. I don't know about you, but I need people to help me with these variants of unknown significance all the time. We all need that a lot. In other words, you see it, but does it matter? And so this is useful for this particular reason. The reason why I'm talking about NF-kappa B1 is, gee whiz, NF-kappa B1 is downstream from cytokines, chemokines, adhesion molecules, apoptosis, pro-inflammatory, IL-12, IL-23, cell cycle regulators. How can this show up as a CVID patient at the age of 20, 30, 40, or 50? How can that be? You have a mutation in all of these pathways at the same time, and you're telling me that they come in with just a B cell deficiency? That's what's so odd about it, And I find that just completely kind of flooring, and I think we still don't understand, why does the B cell tell you that clinically, when in fact it's absolutely an inflammatory defect, which should be a lot more global than that. This is another very odd one. This one actually arose, Sergio Rosenzweig were at the summer school, and I said, we have a patient with an Icaros mutation. He said, it's funny, I do too. And so at the time, then we put together this report, and with a lot of other helpers, obviously, Bertrand Boisson at Rockefeller as well. But the point is that Icaros, which should in a mouse give you no B cells. If you have an Icaros mutation in a mouse, you don't get any B cells. But the patient that I'm talking about here, my patient, is actually a nursing student in Connecticut. She's 25 years old and she's in nursing school. And so she's got an Icaros mutation, and it's an interesting thing that you can have something that should have wiped away your ability to make any B cells. And I'll show you there's even more that Icaros does as well. And yet it looks like this. And the other curious thing about Icaros is it can exert its opinion later in life. In other words, you can have an Icaros mutation that you are born with, and you may not notice that it's actually causing any hypogammaglobulinemia until 20, 30, 35, or some years later. It's an interesting one. So we actually have 3 or 4 patients. I'm just going to tell you about 3 of them right here. One of them is this, I guess the 23-year-old one up there who had been diagnosed previously. She's extremely immune deficient. As you can see, she has no B cells herself. She's very, very immune deficient, but she's 23 when she's diagnosed. The one over on the side is a 33-year-old lady who previously had autoimmune hemolytic anemia. By the way, she's a product manager at Pfizer, and she actually has a mutation in Icaros. She's a patient of mine. And this 29-year-old male had a T-cell leukemia at Yale when he was a little boy. And his mother said, "You're not doing a bone marrow transplant." She said no. He survived. And he shows up at the age of 29 with miserable diarrhea in our clinic. And of course, he's completely hypogammaglobulinemic, and that's the reason why he has an Icaros mutation. So in other words, your past history will be odd and interesting. Now his is in the dimerization domain. So it could be his phenotype is different, partly because of the location of the mutation. You could always think that's the case, but we don't honestly know. But the thing I'm trying to say about Icaros is that why would it look like a B cell deficiency when it actually controls so many other genes? And that's what I find just completely kind of, a stunning idea that I don't understand. Why did B cells take the hit when in fact it's not even their fault? You know what I mean? Not their fault. It's some other gene, it's got nothing to do with B cells in particular. So when you see a patient, you just honestly don't know what you're going to find. You're going to see some unusual genes are going to crop up, and we're not done yet. We'll see some very odd ones, even more coming up soon, very soon. So just kind of cutting to the chase here. We took about 235 of our patients from Mount Sinai, and then we collaborated with Lennart Hammarström in Sweden, and he took 128 of his patients that had been sequenced, and then collaborated with Hassan Al-Bassani in Tehran, and he took 235 of his Iranian patients. All of these patients look like CVID. You would think so, I would think so. They could walk into this room, we would say it's CVID. What is the gene? Actually, it's 56 different genes in 601 patients. A huge number. Now, I've tried to color code them a little bit. So the pi for me, TACI mutation is the biggest one, NF-kappa B1 is number 2, and CTLA4 is number 3. But you can see that color coding that to the Swedish population, Lennart did not see as many TACI deficient patients. He didn't have any CTLA4, and he had a little bit of NF-kappa B1, and it was quite different in the Iranian population. So it's going to depend upon the population that you see. In other words, where you actually dwell. I took the slide out of Freiburg. Freiburg actually has published their data as well. The Freiburg data from Germany looks very much like the US data, as a matter of honest fact, and very different from the Swedish data and very different from the Iranian data as well. But here's what I want to say is that in the United States, most of them that give you CVID are what we call autosomal dominant. I just said dominant, but you don't get a family history most of the time. How can they be dominant if you can't get a family history most of the time? And that's because that's what the NF-kappa B1 and the TACI and the CTLA4 mutations actually look like in a family. They're not breeding true. There's something strange about the fact that they may or may not appear. We have to cope with that. The Swedish population was a little bit more recessive, some X-linked, and the Iranian population, as you might expect, it was much more autosomal recessive. So in other words, a lot of pathways that you can get to a B-cell deficiency disease. And now I said a moment ago that we like this system, and I very much love to be on the IUIS committee. It's such a wonderful group of people. And I do believe in dividing things by phenotype. The catch is, where were the genes that give you CVID? They didn't think they wanted to sit in the table 3. They didn't feel like it. What they felt like is wandering all over the map here. You see, so that's the curious thing about it, is that it could be anywhere along this entire pathway. It could be a combined immune deficiency, and believe me, we have a couple of patients with RAG1, RAG2 who are adults. I'm sure they're at work today doing whatever they're doing, and it should be a SCID, but it wasn't. It's actually a CVID phenotype. So the phenotype is one thing, and the gene type is going to be another. And I find this to be, just one of those very curious things. Immune dysregulation, look down that number. Defective intrinsic and innate immunity, inflammatory diseases, and moving on down. It's just very odd, isn't it? So all of these, you can never know what you're going to see. Now remember, though, that I said 30% of the time you'll get a gene, 70% of the time you will not. So you have to sort of memorize that fact too. It's worthwhile looking. On the other hand, you may not find it. Anyway, you open this hefty bag, and what do you find? And these are some of the things you see: the TACI, the NF-kappa B1 and NF-kappa B2 I didn't talk about, CTLA4, LRBA, STAT3, Icaros, strange things. BOC2, TCF3, even WIM. We have a paper that just came out in the fall about patients carried at Cornell University for 20 years for hypogammaglobulinemia, actually have WIM syndrome. That's actually what it is, CTLA, that mutation in CXCR4. I don't know why you have 3 there, it's 4. And some X-linked defects as well. So you're going to find a lot in that bag. And they're due to genes that are really could be found in pretty much any area of the development of a B cell, starting with what should have kicked off a stem cell and allowed it to not even be progressive into anything, and moving on over into the final one over there I find very interesting is April. The one that you can see right on the end. Reason why I think is April is interesting is that this is just some Japanese patients that were found to have a mutation, I think recessive mutation in April. And what they do is they make antibody, they make immunoglobulin, they have B cells, they have memory B cells. Can't make a plasma cell. Sorry. I can get to the memory B cell, but I'm not making you an antibody. And I never remember anything, by the way. And so you look at the antibody a little bit later and it's gone. So in other words, you can't finish that last job. It's a very interesting phenomenon. So that's why, you have this kind of amazing history of B cells. This is not my slide, it's McKaiser-Williams. But the point is, what does a B cell go through in order to do this amazing job? Which is that it has tremendous amount of interactions which have to occur. It has to migrate from one region to the other. It has to commit, it has to get the right cytokines, it has to get the right adhesion molecules, it has to go through affinity maturation. You have to somehow get all of these things to coordinate with each other. And then finally, antibody secretion. And even after you've done that, you have to establish this long-term memory, which is just an extremely difficult job, which we still don't really understand. You can have patients who will make an antibody. What is antibody deficiency? We call it antibody deficiency, right? It's still a category we can call normal immunoglobulins with poor antibody retention. It's still an ICD code. You can use it. You can get gamma globulin with it. What is it? What is it? It's going to be molecular. We just don't know what it is. So what else did we learn? I think one thing I'd like to say, first of all, is that the deleterious gene effects were found in people of all age groups from 5 to 75. And I've color coded them. So you can see the patient born in 1947, so she's well into her 70s up there. She actually has a mutation in NF-kappa B1, a frame shift, which is no joke, a frame shift in NF-kappa B1. She's 71 years old. Yes, this is what's wrong with her entire life. She's had a pneumonia or two. She has pretty bad gastroenteritis of times that have been bothering her. She doesn't weigh very much. She's been anemic at times. She's had ITP once or twice. But that's what she is. She's 71, and this is the reason. And she's now 71. So don't think that this is a childhood ailment. It's not. This is any age, I'm speaking to the internists, but also just trying to make the point that you don't skip genetics just because somebody is older. So anyway, they're color coded. The other interesting thing is you can see we have a couple of Kabuki patients in here. So in other words, that's really not an immune gene, but Kabuki patients will show up in your practice as well. They have ITP, they're a little bit slow, maybe. They're a little bit hypogamma, but that's what it is, actually Kabuki syndrome. So the age doesn't give you a clue about the gene. And the other thing is the clinical phenotype suggests you're going to find a gene. And I think I've said this morning to some group of you that, I have patients that, oh, somebody has a big spleen, they have ITP, they've had, bad gastroenteritis, they have some granulomatous disease. They'll say, oh yeah, right, that's going to be a CTLA-4. That's going to be a this or that, the other thing. Is that likely? Actually not likely, which is that overall 30% of a gene we could find that was P causative, 70% didn't. Did we find autoimmunity? A little bit more likely that we're going to find a gene? Yes, P.01, 02, I guess, probably not much, but somewhat. The patient has bad pulmonary disease, you're a little bit more likely to find a gene. If you find liver disease or granuloma, it's a little bit more likely, but it's not a slam dunk. You oftentimes will not find that. So we published this in Frontiers. It doesn't guarantee you're going to find a darn thing, which means, of course, keep looking because we don't know the answer yet. So the clinical phenotype doesn't tell you you're going to find a gene. I guess one thing you might be wondering is, why do I spend so much time looking at the genotype? I'm going to give them gamma globulin anyway. Just be quiet and give gamma globulin an antibiotic, and that's the end of that. Why spend their money? Right? Are you wondering that? You're wondering that. Okay, well, I'll give you a few reasons. And they're not wonderful reasons. One of them is that I just love B cells and I like to know how come they work. But my intellectual curiosity has nothing to do with their payment. Okay, so I understand that. For this great number of patients, this is what I spend most of my time working on, right? For 623 subjects, you have infections, but a whole lot of other things. Okay, yeah, they have infections, but what else do they have? Well, autoimmunity, chronic lung disease, lymphoid hyperplasia, gastrointestinal problems, liver disease, granuloma, and lymphoma. So it's not like the patients have a scot-free life. They don't. They have a lot of disease. You're familiar with these pictures, I think, right? Bad lung disease. Do I find a gene every time? No, I don't. Granulomatous disease, maybe sometimes, maybe not others. GI disease, a lot of GI disease, a lot of liver disease. These patients have a lot of inflammation. So this is what I am personally interested in. And that's what I was telling some of the others, you know, what we're doing about this, which is kind of a whole new topic. I'm not getting in today what we're doing today about that. But the point is, can this help us? One thing I have to mention is those, when you do see one of these complications that I just mentioned, the likelihood that they will survive is clearly reduced. There's 11-fold mortality within the next, 25 years. Let's put it that way. If your patient has very low isotype switch memory B cells in any of these complications, the chances that you will live to see them get married, have kids, becomes diminishing, right? For them to have grandchildren, perhaps invisible, perhaps not happening at all. So it's up to us to say, okay, what do we not know? What more do we need to know? These patients need more of our attention, not the ones that we can do genes on. I thought genes would solve everything. I really did. 10 years ago, I thought we'd do just genetic sequencing, end of story. It didn't work that way, not yet. So that's why we have to continue to say, what else, what else, what else? Well, this is what else. This is an example. For example, this is a 19-year-old girl with progressive lung disease and enteropathy. ITP, lung disease, infiltrates, no organism that I could find, some non-caseating granuloma. She's a little bit hypogamma, not astronomically, but she doesn't make antibodies well. GI biopsy shows villus atrophy. And of course, she has a mutation in CTLA4. She is one of those in which it became true. And so what do I have her on? Well, I have her on an interferon, an inhibitor of CD80, which is going to be abatacept. This is the accepted treatment now. If you find a mutation in CTLA4, this is a treatment that actually does work. We borrow this from the rheumatological group. It's not easy to get permission, by the way. I find it kind of hair-raising to make it happen. But finally, you can usually get your way. So she's on Orencia, which works out. It helps her out. Her GI disease is much better. So in other words, I do have something that can help her. This doesn't happen very often, but it does happen. What about this lady? She came to me from the University of Pennsylvania. Frequent infections, followed at Pennsylvania for a long time by one of the clinical immunologists at Penn. Very, very hypogammaglobulinemia, previously had a splenectomy, granulomatous hepatitis, prednisone, methotrexate. She's been on a lot of medications when I first saw her. She's almost got no T cells at all, except for the ones that she does have decide to wander into her liver, and it's an oligoclonal T cell population. And she ended up dying of liver and bone failure. Well, I'm one of those people that saves DNA, and we ended up finding out that she has a compound recessive gene mutations in LRBA. She should have been a candidate for the Orencia, but by the time that I picked that up, it was too late. She had gone. So in other words, it tells me what I would have done better. Tell me what I could have done better, should I have known that in advance. So this would have made a difference. Would have made a difference for me to know that. This is an interesting molecule, lipopolysaccharide responsive vesicle tracking beach and anchor domain. I know it's a terrible name. Anyway, it has to do with recycling cellular components. And basically it has to do with the connection with the CTLA4 molecule, and the treatment is actually just the same. So in other words, this would have been her treatment had we known that. This is a patient of ours, 20 years old, from the age of 5, hypogammaglobulinemia and enteropathy, interstitial lung disease, splenomegaly, lymphadenopathy, a mutation in the PI3 kinase gene in her case. And then she developed B-cell lymphoma, Epstein-Barr virus treated with rituximab T-cell therapy. She had a bone marrow transplant at Sloan Kettering, and she expired. By that time, I knew what the mutation was, but the compound had not yet been licensed for clinical use. So she did never get the ability to be on the compound lestolinib, which we would have put her on today. So that would have been the appropriate treatment, but we didn't know it at the right time. So in other words, these are situations in which we actually have a pharmacologic, can actually be of some use. This is another similar one, 20 years, numerous medical problems, a sports manager, diabetic on the insulin pump. He's had ITP, refractory infections, enteropathy, growth hormone deficiency. You can clearly see there's a lot going on here. IgA deficiency, lack of antibodies. Said to have CVID because, hey, we needed gamma globulin. We had to put a name on that thing somehow. Put out CVID, put him on gamma globulin. He has a spleen, which is huge. And his mutation, one of the gain of function mutations in STAT3. And so what do you think he's on? JAK inhibitor. Yeah. So that's basically it. So what he does is he makes too much IL-6, not enough IL-10. And he has this inflammatory response, and we have him on a JAK inhibitor, and it's now 3 years later, and he's really doing really quite well. Is this a lifetime thing? I think it may be. I don't have a better answer for him right this moment, but at least a start. So these are pharmacologics. Is it common? No, it's not common, but if you find it, you're going to be happy to find it. So it's worthwhile the doing of it. And this is another situation a little bit similar, which is a 33-year-old guy that I met during the COVID period. I didn't actually lay eyes on him. We had a virtual interview. He's in Ohio. I'm in New York. I know he's very hypogamma. I have all his paperwork. I arranged for he to be tested for all the genes that I can think of. He has a mutation in TCF3. The mutation is one which is 554, asparagine to a 554 serine, which looks quite deleterious, although it's called a VUS, by the way, please notice that. On the other hand, it's the amino acid just adjacent to the one that was in the Journal of Experimental Medicine that says this is a deleterious mutation. And so obviously that's the reason that he is hypogamma-globulin-emic. He has the TCF3 mutation. And TCF3 is important for normal B cell development. It's in B cells anyway. Kind of an exception to the issues of things where things are not in B cells. This one does happen to be in B cells. But the good thing about this particular workup in his case was that his 4 children do not carry the gene. Now, how that happened, I couldn't tell you. All I know is his kids don't have it. So in a way, it was a bit of good news for him. So in a way, it won't just be what you can do for the patient, but what you can do for the family. In other words, other family members are going to need to know what you have just discovered. So he's a little bit of a lucky guy. I guess I just have one more. This is another situation. Again, a very odd gene. This one is a very hypogamma-globulin-emic lady who has miserable diarrhea, the worst you've ever seen, and treated for Crohn's disease for a very long period of time. She's anemic. She's on TPN. She's treated with rifaximin, budesonide, nutrients, TPN, everything you can think of. And she has a mutation in the gene called BOC2. And I didn't put anything on BOC2, but BOC2 actually was reported in Nature Medicine a few years ago as being a regulator of Tregs. And so her treatment now is sirolimus, and she seems to be doing much better on sirolimus. Again, picking the inhibitor that suits the pathway, gave her a bit of a better chance. Is it perfect? No, it's not perfect, but she's gained weight and she's at least now stable. So this is the workup that we used to do, right? You see a new patient, what we would do, and this is just the way I've always done it, Sloan Kettering, when I was first there, moving to Mount Sinai, what we would do, you'd do a CBC, you do a lymphocyte panel, lymphocyte screen, you do complement, and then IgG, A&M, and a bunch of antibodies and call it a day. That's the way we always did it, right? And then finally, if you didn't get your way, you'd finally consider genetics. You'd think, okay, maybe call the patient back, maybe do it again. I don't know about it, you guys, but to me, I've begun to switch my view, which is that I would do the genetics sooner than later, and I think that's possibly the way that the world is going too. In other words, you see something a little bit complicated, little clinical syndrome that's quite difficult, an answer that you need sooner. Somebody who's come to you, who's taken a bit of travel time, you want to do what you can for that patient on that one day. You don't want to spend, their time coming back again another day if you can. So we tend now to do genetics earlier than we used to do them for the same reason. And especially with CBID, because I think it's still a box that we need to open. It's still a hefty bag. There's a lot more in this hefty bag. So what did we learn? Well, a lot of genes, a lot of causes for the clinical manifestations. Sometimes they will suggest to you a treatment. You'll be lucky if that's true. It doesn't happen all the time. Most of the time, it doesn't happen. On the other hand, you'll be very, very happy when it does. Family considerations. And then, when you are looking at, we've had this happen a million times, you'll get the clinical report will say it's a variant of unknown significance. What can you do about that? I'll tell you what I do. I look at the gene and I do a PubMed and I say, who loves that gene? who's working on that gene? And then I call them up or I email them and I say, you know, I have a patient with a card 11, you know, what do I know about card 11? Not my gene. You know, but there are people out there who love card 11. We had a patient with ligase 1. That's the only way that I have a ligase 1 paper with Patrick O'Brien at University of Michigan. I've never met him, but he and I are close collaborators. So, you know, there's somebody out there who loves that gene and can help you out, and they probably will, because they want to know what they need to know too. That this is a pathogenic possibility. And then, of course, you're going to have to revise your reports. And then, of course, we've got to seek new genes. And I put this one in there because this is where vaccination started. Have you ever seen this picture before? This is the backyard of Samuel Jenner's house in Bartlett, England. And you can go there and you can take a picture of yourself in the doorway of this place too. And the reason why it's in the backyard is because Mrs. Jenner said, "You're not doing it in my kitchen." It's true. That's a true statement. This is the first vaccine laboratory. Because Mrs. Jenner said, "You're not doing it in my house. You can do it in the garden." Samuel. And these are some of my fantastic collaborators, first of all, at Mount Sinai. And I should say at Rockefeller with Jean-Louis Casanova and Bertrand Boisson. And Stanford, Scott Boyd has done some wonderful work with me. If you don't know Scott Boyd, you should. He's fantastic. Eric Meffrey, unbelievable scientist, wonderful guy, and the Karolinska Institute. So thank you very much. And thank you, Dr. Wasserman.
Wonderful. Thank you for the outstanding talk. Very inspirational as well for trainees to think about pathways and immunity and how it can really manifest potentially in patients. Obviously, you pointed out many unknowns, got more confusing in some ways. So we have maybe a few minutes for questions if anybody has. Dr. Ghosh, of course. Great. Dr. Wang? Great. We have to wrap up, but I think we're going to hang out for a picture for our divisional picture. So those of you in allergy immunology, do not leave yet. And Dr. Wasserman, thank you so much for everything you've done for all of us here. And thank you, Charlotte, so much for the wonderful lecture and spending time with us. All right. Have a great day. Thank you.